All right. Yeah. So my name is Matan Kushner. I'll be uncovering the magic powering your favorite real-time experiences using the magic of CRDTs. Um, so this is a bit of a wordy English talk. So uh, no hard feelings if you don't feel like you can keep up. Um, but for those of you who do, you're in for a treat. Um, so gone are the days of building synchronous, single-user tools. In the last decade, we've seen Word get replaced by Google Docs, and email being phased out in favor of Slack. Sketch is being replaced with Figma. More and more powerful tools are coming to bridge the gap between in-person collaboration and remote collaboration. So before we get into this, I'd like to quickly introduce myself. I'm Matan. I'm a full stack developer based out of Montreal, Canada, usually. These days, I'm in Tokyo, escaping the freezing cold winter back home. In English language, I'm a developer at AniList, which is a social network and encyclopedia for anime and manga by speaking fans. I'm also oh goodness, about I've got bad luck today. Happened to me. Uh, hmm. Here we are. Hello. Sorry about that.
Sorry for
All right.
interruption. Yeah,
No
I'm back.
problem. This happens, I'm sure.
Could you continue this section? And so I've heard.
Yeah.
So yeah,
All
the
right. I'm happy to
presenter's
go. Okay.
internet is wrong, and yeah.
Yeah, I can pick up where I left off. Cool.
Okay.
So yeah, on the side, I'm a developer at AniList, which is a social network and encyclopedia for Western anime and manga fans. And I'm also the lead maintainer of Starship, which is an open source cross-shell prompt written in Rust. Please check it out on GitHub. But none of these are real-time apps. My experience with real-time apps comes from Code Sandbox, where I was a former full-stack developer building the real-time collaborative functionality in Code Sandbox, which is a real-time developer environment for teams. Today, I'll be talking about some of the techniques we would use at Code Sandbox and which they're using today to power real-time collaborative features. At the core, they're CRDTs. Well, what are they? The jargony computer science answer is conflict-free replicated data types. For a person without an academic background in math or in computer science, this tells me very little. Another way to put it is that CRDTs are a kind of data structure that can be cleanly merged with others like it. So in the case of a text document CRDT, where we can take the edits of multiple users and cleanly merge them together. The conflict-free part of CRDT means that it won't be a jumbled mix of words mixed with one another. It'll resolve to something coherent. You'll have full words in this context, and it'll best reflect the intent of the users who wrote it. In this talk, we won't be talking about text specifically, but we're going to be turning a to-do list into a real-time application. We also won't be covering things like real-time networking or offline storage methods. Each of those deserve their own talk. Instead, we'll be talking about the underlying structure of a CRDT to make mergeable structures. So let's look at this to-do list. On the left, we have the view. This is what the users see. The to-do list itself. Write the JSConf talk and create the slides. And now I have yet to give the talk, which is what we're doing now. On the right, we have the state, which has an array of objects because we have a list of to-do items. And each object has a title and has a status. So how do we turn this into something that is offline capable or real-time capable? Well, we need one more data structure, and that is the operation log. The operation log is a step-by-step list of changes that are made when a user's offline. So if I disconnect from the internet, I change some to-do items, and I reconnect, this list will be sent to the server. So it looks a little bit like this. If we were to recreate the application state, the log is create an item at index 0, create an item at index 1, and one at index 2. Here's the list. And then if ever we make a change, it'll look something like this. 2 new entries are made to update the status of index 0 and the status of index 1. What's cool about the operation log is that it allows the application state to be perfectly reproducible. By going through this step-by-step list from top to bottom, we will end up with the exact same application state. So in that way, anyone who connects to the real-time application can be caught up very quickly by just being sent the operation log naively. It doesn't need a lot of fancy logic. So in this way, our state is deterministic. Now let's take a look at collaboration. When changes are made in the operation log, like I said, they get sent to the server, and the server will propagate that to all the other clients. And in that same way, if a client who's connected makes a change, it gets sent to the server, and we eventually get it along with every other user. So that goes on to update our application state like so. with our latest update, our application state is now up to date. That's it. That's the bread and butter of CRDTs, or the general structure. Now, if only it were that easy. CRDTs, well, the mental model looks that way, but let's take a look at perhaps how synchronicity works, or how data syncing works. In our heads, it looks a bit like this. We have the server in the middle, and users are able to push changes to the server at the moments they need it. The server sends it to the other users. In reality, though, unfortunately, it looks a little closer to this. Once operations are sent, there's no way to know for sure when they'll arrive or in what order they'll arrive. Request timings can be affected by payload size, by network speeds, network saturation, latency. We can't be assured of the order of operations. So that will introduce some potential problems. This is further exacerbated by not only the connection to the server, but by the server's connection to other users. Now we're left with a mess. We need to create a structure that is resilient to this kind of mess, that makes so that the order doesn't really matter. So let's look at a what-if scenario. We've got Alex, who creates a new entry to the list, do the laundry. And then before that's received, Jade also creates an entry to the list called buy white bread. Now, by the time Jade receives it, Alex has then created another entry to update it to complete it. And only after all of that does Alex get Jade's changes. I'm sure you can see from here what's going on. Can you guess what they'll both end up with at the end? So at the end, Alex now has Jade's initial to-do item, and Jade has Alex's completed to-do item. They are fully diverged. Both have completely different states. And in the future, operations can just make this worse. It's very hard to recover from a situation like this, because now they're working on different assumptions of the application state. This is the worst situation for a collaborative tool, right? So what can we do to prevent divergence when designing a real-time application? We need commutativity in our operations. That's a mathy word, but the idea is that operation order shouldn't matter. As long as all users receive all operations eventually, they should end up with the same state. So let's look again at our application state. In our case, the main culprit was that they were both creating new entries on the same index. Indexes were the source of problems. So in our case, to be able to make it commutative, we can't be using indices like this. To ensure that they're commutative, we needed to give items unique identifiers that are resistant to this kind of mix-up. Here we're now using CUIDs, which are a form of unique ID. You could use any unique ID, as long as no two items can be identified in the same way. And in that way, we're able to avoid this failure. Looking at this example now, where Alex and Jade create a new entry at the exact same moment, both end up with the same merged application state. There's no way for these two to conflict as long as they're talking about items by their unique IDs, right? So let's look at another potentially challenging example. Alex is offline. Now we're going to start introducing offline into the mix. We have one task called cook a pot of pasta. Alex completes the task, makes some pasta. Alex then later eats the pasta. They still need to cook pasta, right? So at that moment, Alex goes online and sends that operation to Jade's side. Jade, on her end, ends up cooking pasta and sends that operation to Alex. Again, we're in a bit of a mix. The IDs didn't really prevent this kind of problem, where we have two users who are going to end up with differing state. Alex on his end is going to maybe see Jade's latest change. So if the pasta was cooked, Jade on her end is probably going to see Alex's latest change, that the pasta is not cooked. So at that point, we've diverged. We're working with different data across users. So we need to think of a way to make this actually commutative. So what can we do to make this commutative? What property led to this problem? In this case, the main culprit was the timing of both operations. They were both received around the same time. So looking at the application state, there's no way to see where a winner is. One solution would be to add timestamps to the operations like this. So now we can see the exact moment an operation took place. In JavaScript, timestamps are millisecond-based, so down to the millisecond, we should know which one happened first, even if it was sent and it took tens and tens of seconds to make its way to the other client. What matters is the moment that the operation took place or the operation was created. So how do we update our structure so that we can take advantage of this updated timestamp? Let's rethink this a little bit. Here, we're going to break up our to-dos into first IDs and title up top, and then we're going to create a new segment for completed on the left here. Completed is going to have the value of the status and also the timestamp of the status. And that's very important because if we get an operation that is old, we can ignore it. If we get an operation that is new, we can update it. That way, we're always working with the latest operation. And as long as all clients are working on the same assumptions of how to prioritize state, they're going to end up with the same application state. So let's look at an example here. We've got Alex and Jade with their old operations. Let's add some timestamps. And you can see immediately Jade's timestamp is just a few seconds ahead. It's a few seconds newer, right? So in that case, we can go ahead and see that it's going to update the state for both of them in the same way. Alex, who's going to have the older operation, is going to receive Jade's newer operation and is going to override it. Jade, on the other hand, is going to receive Alex's old timestamp operation and is going to ignore it, dismiss it because it is an old operation. And in that way, both are working on the same assumptions now. Both are working with the same merged state. So this approach makes it so that this conflict can't arise. But on the off chance that we get the same exact timestamp, so here in this case, we updated it to have both Alex and Jade work with the same timestamp, what do we do then? Well, we have an escape hatch. We have one final resort here, and that is adding an author ID. So Alex has a unique ID, and Jade has a unique ID. And this is used as a bit of a tiebreaker. In the event that we get an identical timestamp, it's going to favor the person with maybe the alphabetically lower author ID. That way, at the very least, both clients end up with the same thing. It doesn't matter the order, really. It just matters that it's the same order for both of them. So in this case, Alex has a smaller author ID. That timestamp will make its way into the application state. Cool. So this process, this whole data structure is called a last write wins map. This is the CRDT solution to a map or a set. And it's a common way to solve these kinds of problems. In fact, there are plenty of applications that use just a last write wins map for collaboration because it's so simple to write and it just works. All right. So looking back at the application state, it's also known as an LWW map. You might see this as shorthand around the web. So looking back at the application state, our LWW map doesn't only doesn't only just work for completed state, binary state like this. We can use it for any number of things like author, assignee, due date, subtasks. If you know of the project management tool Linear, this is actually what they do under the hood. It's a complicated to-do list app, basically, and all they have is a last write wins map for collaboration. That's all they need to make it real time, and it's super easy to fit it all in your head, right? To make sense of it logically. Real time doesn't have to be very complicated. So we've got one more thing that we want to add support for in our to-do list. Let's tuck away completed. It's still there, but we're going to add a new property for ordering, right? If we want to have orders or ordered tasks, how can we introduce those? The naive solution would be to create a new order field and give to-do list items positions with integers. And you can maybe start to see how this can start producing issues. If you have two entries, if you have two entries that are created adjacent to each other, that you might need to use similar positions or change position. Here, let's take a look here. So if you create a new entry right here, what value should that have? If we make it have a value of 0 or of 1, we have to then change the position of other values, of other to-do list items. That gets complicated. Well, the easy solution would maybe be to change these from integers to floats. So that way, we can have a position of 0.5, right? That makes it very easy to just insert new entries between existing ones on the fly. And that's exactly what many applications do. It doesn't have to be complicated. CRDTs can be a very easy way to introduce real-time into your application. So now we got a to-do list working. Let's take a look at the implications of this design. Remember how we had a single server acting as a relay for the application state? Any operation log changes went to the server, which went to other clients. It turns out we never needed the server to do any sort of authoritative decision-making or any kind of validation. Everything just kind of worked. And in fact, in this application, the server can run the exact same code as the clients. The clients just relay operation log changes to the server in the same way that the server just relays them to other clients. This isn't a coincidence. CRDTs help us design not only offline capable applications, but also entirely peer-to-peer applications. This exact structure can be used like this. We don't actually need a server. And that's what's fascinating about CRDTs. Such a simple, elegant solution just works for so many applications. So as long as you have the networking down pat, and you can make it so that you can create entirely serverless applications just like this, peer-to-peer, Bluetooth-enabled, or whatever it is. And there doesn't need to be an authority or a server. So if you're able to follow the core principle of commutativity, you can fearlessly introduce real-time and offline functionality into your app. If this interested you, there's so much more to learn in the space, especially around real-time text editing. State-of-the-art is constantly being improved. The research is public and easy to, like some of the easier research papers to read. Not too academic, but there are a few organizations making it approachable for others. If you're interested, I recommend checking out Ink and Switch. They're a research lab that are working on state-of-the-art for CRDTs in public, and also the website crdt.tech. That is an aggregate of all CRDT research papers and presentations, and is a great way to learn more about how these real-time applications are developed. Anyway, that's really the end of this. If you want to talk about CRDTs, if you want to talk tech, feel free to reach out to me on Twitter @MattChai. Thank you so much for listening, and I hope you have a great rest of the day.